I want to get started by talking about what is energy. What is energy itself? So, the idea is that it is the ability to do work. Okay. Now, work is maybe moving something or heating something up, changing the temperature of something, affecting matter in some way is what we mean when we say the ability to do work. And that brings us to our second objective, which are what are the units for energy? All right. The units for energy are joules. All right. And it's not spelled the way that you think it is. That's Joules. It's a weird word named after some scientist. All right. So that's what joules are. And we're going to draw a picture of what a joule is so that we can better understand it. Now, 1 kilogram, since we're Americans, we don't know what kilograms are. 1 kilogram is equivalent or about the same as 2.2 pounds. Now, a joule is is the amount of work required. Let's write this down. All right. A joule is the amount of work required to move 1 kilogram. All right. Now, how far do we have to move it? Well, we have to move it 1 meter. All right. But what a meter is it's roughly 3 feet, or it's 100 centimeters. Okay. So 1 meter is kind of close to 3 feet. All right. Because we don't use the metric system here in the United States. We have to do these weird conversions because the whole rest of the world uses the metric system. We do not. So going back to this right here, whoops, wrong button. Going back to this right here, joule, 1 joule, is the amount of work required to move 1 kilogram 1 meter. And just so you know, 1 meter is M, mile is MI, and a minute is MIN. So if I say M, that means meter. Okay. So a joule is the amount of energy required to move 1 kilogram 1 meter. So if you were to find something that was roughly 2.2 pounds and you lifted it up about 3 feet, you would expend the amount of energy of 1 joule. Hopefully that makes sense. So now that we know what a joule is, we should draw a picture of one. And that's what we'll do right here. All right. I'm going to draw like a little box. Let me actually grab my... I'm going to draw a little box. And in that box, I'm going to draw what a joule is. Okay. So what I will do is I will draw a picture of me. And I am lifting a kilogram up. So we've got a kilogram. Now, what's important here in science is that we label all of our drawings. That's what makes a drawing a model. And we lift it up 1 meter. All right, so we've got 1 kilogram, and I've lifted it up 1 meter. Let me grab Mr. Fairchild and move him up here so he's moving it. All right. So I have, oh gosh, I didn't label Mr. Fairchild. All right, so I have moved my kilogram 1 meter. I have expended 1 joule of energy. 1 joule of energy. So that's what a joule is. All right, it's the energy is the ability to do work. We measure energy in joules. And 1 joule is the amount of energy required to move 1 kilogram 1 meter. So now that we have that all figured out, let's go back to our objectives. We've got the first part done. We've got the second part done. Now we want to talk about what is electromagnetic energy. Well, in order to do that, we have to look at this weird thing right here. We're going to ignore the light wave on the bottom. And right now we're just going to be looking at the mechanical wave. And the mechanical wave in the classroom, I would shake a spring up and down so that you could see this, but obviously I can't do that here. So we're going to look at this instead. Now let me change color so that we can draw on this. You can see that the parts like this one right here that is moving up and down and up and down. Actually, let me erase that and I'll just use my laser pointer. All right, right here. This I've frozen it, this node right here, and then it goes up and down. All right, that part of the wave just goes up and down, but the whole wave appears to be moving in this direction. It looks like it's going that direction, but it's not. The wave is vibrating up and down. The particles are remaining in place, and the wave moves forward. Okay, this is what we call a transverse wave. Let me label that. All right, this is a transverse wave. What that means is that it vibrates perpendicular to its direction of travel. So in math class, you may have learned what perpendicular means, but basically if I have a line that goes this direction and I have another line that goes this direction, then those two lines are perpendicular to each other. And that is the opposite of having two lines that are parallel to each other, where they go the same direction. So what this is saying, essentially, what a transverse wave is essentially, it means that we have a wave that's vibrating on the up and down along that pink highlighted spot that I just did. Okay, it's vibrating up and down, but it's traveling in a completely different direction. So the part that I just labeled, or I'm sorry, highlighted in yellow. So hopefully that makes sense to you. It vibrates in a different direction than it's traveling. But now that we understand what a transverse wave is, let's go ahead and sketch one so that we have that sketch for later. Okay, so go ahead and grab your pens or pencils, and we're going to draw a transverse wave. Usually what I do when I draw a transverse wave is I start with a nice vertical line like that, and then I draw another a perpendicular line. This is the direction of travel. And then I'm going to change color. Then all I do is this. And it doesn't have to be perfect. All right, in fact, that's actually pretty awful. Let me try that again. Oops, there's a little bit of a delay. There we go. That's a little bit better. So a transverse wave looks like this. It's got that up and down motion like that. Okay, it's vibrating in a north-south direction. In this case, it's vibrating up and down. So it vibrates like this. And we can label that direction of vibration. And then it travels this way. And we can label that direction of travel. So now we know what a transverse wave is. We want to understand why do we care about what a transverse wave is? Well, it all comes down to this very, very important point, which I'll do in very light blue. From here to here. This is called the wavelength. Oops. That's called the wavelength. And what we mean when we say the wavelength is the amount of time, the amount of distance that the wave travels before it repeats itself. So at this point, it's in the middle and it's going up like that. And then it goes down. Here, let me switch to my laser pointer. It goes down and then it comes back up and it's in the middle and it's going up. So that means that it is repeating itself. So So we've got the up, down, up. All right. That's one wavelength. And the reason that we care about the wavelength is right here, the electromagnetic spectrum. All right. Wavelength determines which part of the electromagnetic spectrum that you're in. So if you've got a very, very long wavelength, then you're going to have radio waves. That's what this shows us over here. It says increasing wavelength. Okay. So if you've got a long wavelength, like we're saying bigger than the Earth, then those are radio waves. And you're used to, like right now, there are radio waves zipping through the room that you're in. Your phone. All right. Your phone uses radio waves to communicate. The radio that we listen to, like to play songs, or well, we did when I was a kid, that uses radio waves. The your Wi-Fi uses, all of those things are radio waves. All right. Now we cook with microwaves. Microwaves are called microwaves because when we discovered them, we thought that those were the smallest possible waves. So we said, oh, they're really, really small compared to radio waves, so we'll call them microwaves. And those are the waves that we use in our microwave oven. It shoots little microwaves at it and uses the energy from those waves to heat up the water in the food, which then cooks the food. Then we've got infrared. Infrared is heat. All right. So at Thanksgiving time, you'll be in the aisle at Walmart or something, and you'll see these things that like will cook rotisserie chickens or turkeys and things like that, and it'll say cooks with infrared technology, which is really amazing. Cooks with heat. Okay. Then we have the part that we're most used to, and that's the little tiny blip right here. That's visible light. All right. All of the colors that you see of visible light, they all are in this little tiny section. So everything that you see with your eyes is in this little tiny section. Infrared, microwaves, radio waves are all invisible to us. We can't see any of those. Same thing with ultraviolet, X-rays, and gamma rays. We can't see any of those either. When you get to this side of the spectrum, where we start getting decreasing wavelength, where the wavelengths are getting smaller and smaller, ultraviolet, bad for you. That's the stuff that you want to use sunscreen to protect your skin from. If you get too much ultraviolet radiation, which comes directly from the sun, you get a sunburn. All right. X-rays, they can travel through your skin, through your muscle. They cannot travel through your bone, which is why when you go to get an X-ray, they will they'll shoot X-rays at you, and then it goes through everything except for the bones, and then they can see what's wrong with the bones inside, and maybe if you have to have surgery or get a cast or something like that. And then gamma rays, those are what make the Hulk. All right, everybody's favorite green friend. So if you look at, and this is all on your reference tables, all right, if you look on this scale right here, everything to the right has a long wavelength. All right. So over here we've got, and I'm going to have to change the color, long wavelengths over here. And then over here we have short wavelengths. So if I were to draw this, and let me change the thickness of this. So what I would do is there we go. I would draw the waves like this, and you can see that they're getting longer and longer and longer as we get over here. This is obviously poorly done and done by hand, but you get the picture, I hope. All right. Now, the same thing that applies to the overall electromagnetic spectrum, where we've got short wavelengths over here and long wavelengths over here. The same exact thing applies to the colors. Okay. We've got long wavelength colors over here, red, and short wavelength colors over here, blue. So red has a longer wavelength than orange, which has a longer wavelength than yellow, which has a longer wavelength than green, and so on. Now, hopefully that makes sense to you. So electromagnetic energy, let's go ahead and define that. We'll come down here and we'll define that. And let me get a different color. We'll go with light green. All right. Electromagnetic energy, which I usually just do ELM because that makes it easy to write or shorter to write. And I like to have the ink to be a little bit bigger. This is any energy. That is awful. Any energy transferred as a transverse wave. Any energy transferred as a transverse wave. And there we've got a transverse wave right there. Okay? We can extend that transverse wave just so that we know what it is. So there's our transverse wave, and electromagnetic energy is any energy that is transferred as a transverse wave. All right, our last thing that we need to talk about today is what is absolute zero, and this is super easy, okay? Anything that gives off, anything that is above absolute zero gives off energy. Right now, you're giving off energy in the form of, where is it here? Infrared. All right, humans give off infrared radiation, heat. So if I were to look at you with a or a heat camera, you would, like, the parts of you that were warmer would be brighter, and the parts of you that were colder, like perhaps your nose, your ears, those would be darker. Okay, and like your head would be very, very warm, so it would be very bright in an infrared camera. Okay, notice that there's an extra R right there. Infrared, not infrared. Okay, so an infrared camera is a camera. Let me zoom out. Oh yeah, a camera that can see temperature. Now, the more heat that something gives off, the more energy it will give off. And so what scientists believe is that if you get something cold enough, so cold that it doesn't give off any energy, that's what we call absolute zero. And what temperature is that? Well, absolute zero, and we'll use blue for this, all right? Absolute zero is negative 273 degrees Celsius, or 0 degrees Kelvin. Okay? That's what absolute zero is. It's a theoretical idea that if you get something to this temperature, which we've never actually been able to do, we've got real close, but if you get something to this temperature, then it will be so cold that the atoms won't shake anymore and it won't give off any more energy. All right. So again, these were our objectives. It looks like we got everything ticked, and I will see you guys next time. Thank you very much. And if you have questions, make sure that you let me know.